This next video we'll take a look at 1970 AB3. Consider the function given by f of x is equal to x to the 4/3 plus 4x to the 1/3 on the interval from -8 to 8. And the first thing we want to do is to find the coordinates of all points at which the tangent to the curve is a horizontal line. And we'll get a horizontal line. The tangent will be a horizontal line whenever the derivative is 0. First derivative is 0. And so we'll calculate the first derivative as 4/3 x to the 1/3. Then it's going to be plus 4/3 x to the -2/3. We'll factor out the greatest common factor of 4x to the -2/3. Sorry, that's 4/3 x to the -2/3. And that'll leave us x plus 1 in parentheses, and so our 0 will be at x equals -1. Now this does say find the coordinates of all points, so we really need to plug this back in. Plug in -1 into the first term, we're going to get 1. Into the second term, we're going to get -4. 1 minus 4 is -3. And so that's the coordinate at which we have a horizontal tangent. Find the coordinates of all points at which the tangent to the curve is a vertical line. Well, vertical line is going to mean we have an undefined or a derivative that doesn't exist, but it's a point on the original curve, and we see that happening at x equals 0, which also turns out to be a critical value, and its y-coordinate is 0 also. Now I'm just going to assume here that because they're asking for the point at which the curve the tangent of the curve is a vertical line, that 0, 0 is going to turn out to be a vertical tangent and not a sharp turn. I'm not exactly sure how I would convince myself algebraically in this case that it is, but I'm just going to assume that it is and go on from there. With C, we want to find the coordinates of all points at which the absolute max and absolute min occur. Again, for these we want to test critical values and endpoints. So we have the critical values, we just need to test the function at each of those points. And so we have the endpoints at -8 and +8, and the critical values at -1 and 0. And we'll plug in the easiest way to evaluate a rational function. Remember that 4/3 x to the 4/3 really means 4th power over cube root. The easiest way would often be to evaluate the root first and then raise it to the power. So -8, cube root of -8 is -2 to the 4th power is 16. -8 to the 3rd power again is -2 times 4 is -8. And so f of -8 is +8, and we go in and plot that point. F of -1, cube root of -1 is still -1 to the 4th power is going to become +1. -1 to the 1/3 is -1 times 4 is -4. So we're going to get -1, -3 there, and plot that point. F of 0 we've already calculated already, that's 0. We plot that point. And f of 8, cube root of 8 is 2 to the 4th power is going to be 16. 2 to the 1/3 power is 2 times 4 is 8. And so that's going to give us 24. And from that we can tell our absolute max is at 824. The absolute min is at -1, -3. Next we want to find out where the function is concave down. So we'll need the second derivative. We'll go back to the unfactored form. We're going to get 4/9 x to the -2/3, then minus 8/9 x to the -5/3. Factor out the greatest common factor of 4/9 x to the -5/3, and that'll leave us x minus 2. So we get two potential points of inflection at 0 and at 2. When we plug into the factored form, -1, we'll get negative times negative is positive. Plugging in 1, we get positive times negative is negative. And plugging in 3, we'll get positive times positive is positive. So we see the function is concave down between 0 and 2. And now we're ready to complete the graph. We have the endpoints and critical values there already. We need to have a vertical tangent at 0 and a relative minimum at -1. Function should be concave up between -8 and 0. With a vertical tangent at 0, should be concave down between 0 and 2, and then should be concave up between 2 and 8. But we don't technically have a horizontal tangent at 2. So we see the points of inflection at 0 and 2, the proper concavity, mins and maxes, etc.